Hello, today we are going to continue our work in probability and we are going to be looking at combinations instead of permutations. So this is the formula we are going to be dealing with, and I'm going to show you the formula in practice before we talk about where it comes from. So if we have a look at question 1 part 2, we can see that we're given something that looks a little bit funny. It's like we have numbers written in a bracket. It's effectively what we have. So what we have here is N and OR. So we have 7 objects and we're going to choose 3 of them. So choose is the word that we're going to use for combinations, in the same way as arrange was the word we used for permutations. We'll practice that language a little bit more later. Well, for now we have 7 choose 3, and that's what our brackets here mean. This is going to be one of the ways of writing choose or combination, and in general it's n objects choose or of them. And the other way you will see this written, as I've written it up here, is n c or. And we already came across notation very similar to this for permutations, where we would have had n p or. Now the formula, as I've written it up here, the NCOR is going to be n factorial, so 7 factorial. A reminder again, that means 7 by 6 by 5 by 4 by 3 by 2 by 1, divided by OR factorial, which is going to be 3 factorial, multiplied by 7 minus 3 factorial. So we end up with 7 factorial all over 3 factorial multiplied by 4 factorial. We can put that in our calculator and we'll get 35. So there are 35 ways of choosing 3 things from a group of 7. So if we have 7 objects and we want to choose 3 of them, we have 35 different ways of doing that. Now, we can possibly see a connection between this formula and the permutations formula that we dealt with the last day. So I'm going to rewrite the permutations. This is the question 1 part 2 finished. But if we were asked about NPOR, how many permutations or how many arrangements, it would have been n factorial all over n minus or factorial. 7 factorial all over 7 minus 3 factorial. And that would work out to 210. Now, what's the difference here between these two things? What we've done is ended up dividing by OR factorial. So we effectively have the formula for permutations, how many arrangements we have, and we divide it out by our OR, by the size of our groups that we were taking. And what I want to give you now is an argument for why we did that. So the rest of this video is going to be giving you an argument for why it is that the formula looks like this, why it is we've divided our original formula by OR factorial. And the argument effectively comes down to, in combinations, we don't care about the order of objects. But that doesn't mean a great deal in the abstract, so what I'm going to do is give you an example. So if we took something like what you had for homework, we take the letters of the word maths, we have 5 letters, and we want to arrange 3 of them. So now we're talking about permutations again. We're talking about arrangements or permutations. I'm going to go back to my boxes. So boxes are only for permutations. I'd have 5 choices for I'd have 5 options for my first letter, I'd have 4 options for my second letter, and I'd have 3 options for my third letter. So again, for my permutations, I'd have 5 letters, and I'm going to arrange 3 of them. So take 3 of them. and that's going to end up being 5 by 4 by 3. We've done this the last day. And you get 60 different arrangements that you could have. Now if I look at some of the examples, say if I take the first 3 letters here, as an example, one of those arrangements would be MAT. Another one of those arrangements, taking the same letters, would be TAM, or I could have MTA, or so on. There are 6 of them that I would be able to have. So it will have the same letters, just MAT, but rearrange them in different orders. And I'd be able to do that in 6 different ways. And I count all of them when I'm talking about arrangements, because this arrangement is different to this arrangement. The order matters, so I count these as separate options. But what happens if we don't care about the options that we have available to us in terms of order? So I'd count MAT, TAM, and MTA as all being the same thing because they just have the same letters in it. So if I only care about what letters I get, but I don't care about their order, how would I deal with that situation? Well, I would effectively want to divide out the number of ways that I could arrange 3 things. So I have my 3 letters here, and I don't care about what order they come in. So if I wanted to remove the order, I'd look at how many ways I could arrange 3 objects and divide my original answer by that. So how many ways can I arrange 3 objects? Arrange 3 objects. That would just be 3 by 2 by 1, or 3 factorial. So I have 3 factorial ways of arranging 3 objects. I get 6. So I have 6 ways of arranging my 3 letters for any of the 3 letters that I pick. So if I take my original answer, so I had 60 ways of arranging my letters, and I divide by 3 factorial, I would end up with 60 divided by 6. It's 10. So there would be 10 ways of choosing 3 letters from a group of 5 letters, because I have removed the order of my letters. I don't care about these different ways of writing the same 3 letters. I only want to have M, A, and T in whatever order, and I'm not going to be interested in the different ways that I could write that, the different orders I could write that in. And dividing out by 3 factorial the number of ways I can organize 3 objects does that for me. So that's where our formula is coming from. That's why we're taking our original NP-OR formula and dividing it by OR factorial, because we're removing the order of objects. We don't care about which order our objects come in. To give you an example of the distinction, if we wanted to know how many ways that people in a race could come first, second, or third, it would matter who came first, who came second, and who came third. So the order would matter. But if we're taking 5 cards from a deck of cards, we don't care what order the cards come in. It doesn't matter if a king comes first or third, so long as we end up with a king in our hand at the end. We are not concerned about which card it came out as. Now, the other point that we need to talk about is a funny thing that they have done on the exams. If we look at our formula, the algebra here is going to get a little bit unpleasant, but you do need to follow this because they have explicitly worked with it on the exams, and we're going to look at it in question 21 in a minute in the next video. So if we have this formula here, we know what factorial means. We are going to multiply n by n minus 1. So if n was 10, we'd have 10 by 9 by 8. So we'd have n by n minus 1 by n minus 2 all the way down to 1. So if we write that out, we'd have n by n minus 1 by n minus 2 on down. And I'm going to write something here that's going to make sense in a moment. To n minus or plus 1, n minus or, n minus or minus 1, all the way down to 1. So this is writing out my n factorial. I'm multiplying by n, and every number underneath n, every number smaller than n, down to 1, which we already know from factorial. I'm going to leave or as or factorial for now because I don't need to write it out. And then n minus or factorial would be n minus or multiplied by n minus or minus 1. So whatever n minus or is, the next number down would be n minus or minus 1, on down to 1. Now if we look at the top and bottom lines here, we can see we have a common factor. I have n minus or multiplied by n minus or minus 1 all the way down to 1. And up on this top line here, I have n minus or multiplied by n minus or minus 1 all the way down to 1. So I can divide out all of that on the top and bottom line. And what am I left with? I'm left with n on n minus 1 on down to n minus or plus 1. So the number 1 bigger than n minus or. So if I look at that, and then the bottom line is or factorial on n, or just or factorial, my apologies. So that's what it simplifies down to. Now at the moment that doesn't look much like anything, but you do need to know it in this form. So you're required to know that you can write the combination or the choosing formula in this form, and you're required to be able to derive it in the way that I have here. So we can't skip over that, even though the algebra of it looks a little bit messy. We need to know it in this form, and I'm going to show you why when we're doing question 21 in the next video. The last thing to point out to you is that the choosing formula, this formula here, in this form is on page 20 in your log tables. And it's part of the binomial expansion formula. That's why it's in your log tables. The permutations formula that we looked at the last day is not in your log tables, and because you need to know the choosing formula in both this version and this version, you really need to know it by heart. But in case you panic in the day, the choosing formula is on page 20 in your log tables.